Hi everyone. Today I'm gonna tell you how to solve the two remaining problems from tutorial 12. So it means that it's gonna be the last part of tutorial 12 at last. So, but this topic is relatively easy, and so if you mastered the technique of finding residues of functions in singularity points, this topic won't seem difficult to you at all. So, this is tutorial 12, part 5 at last, the last part 5. Here I'm going to cover two problems, question 6 and question 7, which are in your tutorial sheet. So let's go it one topic at a time. So the first topic is actually these two problems can be viewed as application of complex number variable theory to the task of calculation or evaluation of real integrals, which seemingly don't have anything to do with complex number theory. But let's start with the first one. So integrals of the form integral from minus to plus infinity of some function f of x dx. As you can see, you probably immediately recognize these integrals. You had to deal with them in the past, in quite a distant part, before you knew some new things about complex number theory. You didn't even realize, probably you didn't even suspected that this theory even exists. So what does the complex number theory have to do with this integral? It turns out that if you try to calculate this integral using traditional conventional methods, sometimes it might be quite a long story, quite difficult, so many calculations, so many transformations involved. But if you try to launch yourself into the complex variable space, all of a sudden things might come much easier. And so for this particular kind of integral, there is a very good algorithm. By the way, this is question 6. I wanted to point it out to you. So I think that the best approach is to write you this algorithm, just how to deal with this particular kind of integrals, if you ever come across them. So the first step is change your variable from x to z. Just change letter x for letter z. That's it. Immediately you will get where z is always associated with complex number z is equal to x plus yi, of course. So it means that we launch ourselves to the complex variable space. What next? Then the next step is to check. There is a very nice theorem, very beautiful theorem, which allows you to calculate these integrals, but there are some restrictions. There are some limitations as to where you are allowed to use them. That is why we need to check this condition. Check that your function, which is under the integral f of z, tends to this expression, some constant a divided by z to the power of n, when modulus z tends to infinity, where n should be bigger or equal than 2. So this is a very important requirement. Only under this condition you can use the rest of the algorithm. So we are going to discuss it a little bit later, how exactly you should do it technically. But now just bear in mind that you need to check this condition first of all, before plunging into some calculations, transformations, simplifications, and so on. So the next step after that will be find singularity points. Find singularity points of function f of z. Find singularity points of function. This task is quite pretty familiar to you. Hopefully you don't have any problems with that. Then you will get some number of singularity points, maybe 2, maybe 3, or maybe 1 sometimes. So you need to pick those out of this singularity point, for which imaginary part imagine a part of this zk, let's denote it by zk, is bigger than 0. So what does it mean? It means that if you measure a part of your point of your number, complex number, is bigger than 0, it means that they lie above x-axis. That's what it means. So you are interested only in these points, which are located above x-axis. Such is the condition of this theorem. Okay, finally, the final step, it turns out that your integral of f of z dz, I'm not writing anything about the limits of integration, actually is equal to 2pi times sum of residues of your function f of z in these singularity points which which are located above the x-axis. And summation is done by the index k. So that's the technique. So as you can see, the technique, the algorithm looks very easy. The only thing which you need to check all the time is the requirements under which this theorem is true. Okay, so that is why I think that before showing you some example, I need to discuss this step 2 in more detail probably, because maybe you are not aware how to. So clarification, let's call it clarification. Clarification of some points in our very simple algorithm actually, clarification. So clarification of step 2, how to how to find out that your function f of z tends to this expression a times z to the power of n, and we need n being equal to equal or maybe bigger than 2, but this does not matter. So how can you determine this? I think that you should be familiar with this technique when you studied limits, but let me show you just example. So for example, let's imagine that we had function which looks like 3z squared, for example, plus 5z plus 7 divided by z to the power of 5 minus 7z cubed, and what else, plus 10. So let's imagine that we are having this function under our integral, and we want to explore this thing, either it's true or not. What should you do? It turns out when z or absolute value of z tends to infinity, out of the whole expressions given both in the denominator, the most important term is the one with the biggest power. So it determines the behavior of the whole denominator. So you can easily leave only the biggest power out of three terms here. And the same reasoning should be applied to the denominator. The whole denominator actually behaves like the terms with the biggest power with this one. So we are just, ignoring the others. And after that, you see that you can rewrite it as 3 divided by z cubed. And that's exactly how your function, we should write this guy here. And that's exactly how your function behaves when z tends to infinity. So what can you see? You can immediately see that n is equal to 3 here, because and it means that this particular function would satisfy this theorem, because 3 is definitely bigger than 2. So this is the example of how to determine the behavior of your function. This is actually behavior of function at the infinity. So that's it. I think that we'll have a chance to do more of this in the coming examples. So I'm not going to give you one more example. Okay, so this was the first example. The next, so we discussed step 2. Another step which needs some discussion. So why? No, it's not this actually step. It's the question rather why we can do this at all. Why this algorithm true? Why are we interested only in the area in the region of the plane which is above x-axis? It turns out that such is the layout of the theorem. So it was proved in this theorem. If you take a contour like this, which consists of the half of the circle and the segment of the axis line, so it will be the closed contour. But this closed contour has some certain radius r, of course. But if you start, moving your r to the infinity, this circle, this half circle, becomes actually turns into the area which coincides with the half of the plane, the region of the plane, the part of the plane which is above the x-axis. So for more details, I don't have enough time and to tell you about the details of this theorem. I think the best idea is to turn to your study guide, page 212. And so there is a section 444 which is called evaluation of real integrals. Evaluation of real integrals. So in the very beginning of this section, real integrals, this justification of these techniques is given to you. Maybe if it's not, even if this is not enough for you, please watch your lectures again. This should have been explained to you in more detail. Now I'm just giving you the whole idea. Okay, so it's time for us to apply this algorithm to some particular problem. So let's start. Let's call it example 1 again. Example 1. And so it will be the integral from minus to plus infinity dx divided by x squared plus 4, and all this expression is squared as well. So as you can see, this is a typical integral which you used to learn in the past, but now we are going to apply more advanced techniques. So according to algorithm, what do we need to do? We need to change a letter x for letter z. Let's do it. And we can immediately write our function of complex variable this time. So it will be z squared plus 4 squared and all this in the denominator. So what next? According to our algorithm, we should assess the behavior of our function. This is the step 2, which was just discussed before. So the most difficult, the most maybe strange part of the algorithm. We need to assess the behavior of our function when z tends to infinity. Okay, let's write it down. So we are going to tend our z to infinity. What can you do? You can apply the same reasoning. You can see two terms here under parentheses. Z squared is the first term and 4 is the second term. As was noted before, the behavior of this whole expression inside the parentheses is determined by the term with the biggest power, which is undoubtedly z squared. That is why you can just disregard 4, and you will end up having 1 divided by z to the power of 4. And of course, you realize that n is equal to 4, which is obviously bigger than 2. So the requirement of this theorem, of this formula, is met, and we can move further to the next step of our algorithm. The next step says find the points of singularity. I think it's better to rewrite our function somewhere here. And we are very lucky with this expression because probably you recognize this expression. It could be viewed as formula z. It could be factorized actually, z plus 2i times z minus 2i. And of course, each term should be squared, as the original expression was squared. And so we can immediately see the singularity points. So the first one is 2i, and the second one is minus 2r. Now, according to the third step of our algorithm, or maybe to the fourth, we need to find those which have imaginary part being positive. But I think the better idea is just to plot both of them. So the first point is 2i, it's somewhere here, and minus 2i is somewhere here. And we are interested only in those which are above the x-axis. So we are not interested in these guys at all. Let's cross it off. So now all we need to do, we need to calculate the residue of our function in this point. Let's put a frame around it, and then apply our theorem, which is actually a residue theorem for calculation of contour integral. Okay. But how can we calculate the residue of the function in this point? The best idea, as you know from my previous videos, would be to expand our function into Lorentz series. But you know what? It's not very convenient because the best situation when it's relatively easy to expand into Lorentz series is when your singularity point is 0. that is why this is the case. This is the situation when you don't need to come up with a new variable. You don't need to make any substitution. But in this case, we are dealing with this point, which is 2i. And that is why it's better maybe to turn to method 2, so-called method 2, because there is a suspicion that our point would be pole of order 2 probably. Let me remind you this method 2. So according to this method 2, you should look at the function as being in this form. So if you observe, if you notice that your function looks like this, where necessary condition phi numerator at the point of the 0 is not equal to 0, then you can make a conclusion that this 0 is a pole of order m. So it was a very nice method of determining the poles, poles. And if we manage to determine that our singularity point is a pole, we have a very nice formula as well. I can't say that it's very nice, but it's relatively easy. So let's have a look at our function from this point of view. But unfortunately, I'm run out of my. I need to change to a new page. So what I'm going to do, I'm going to rewrite my function here in a factorized form. So z plus 2i squared, z minus 2i squared, and that's it. So this is my function. And I'm interested in the point 2i, singularity point 2i. And so maybe this expression is exactly what it needs to be in the denominator. So let's try and see this structure behind our function. So as I said before, it looks like this term corresponds to this expression, the denominator. But what about phi of z? It means that the remaining expression, everything except for this red expression, could be viewed as phi of z. We can even rewrite our function placing this factor into the denominator. So it could be written like this: 1 divided by z plus 2i squared divided by z minus 2i squared. So I just moved this whole fraction to the denominator. And this yellow guy definitely plays the role of phi of z. And this red guy, of course, plays the role of the expression which is in denominator. So the suspicion arises that our singularity point, which is 2i, probably it's a pole of order 2, probably. I'm not sure. I'm not 100% sure, because the power is 2, but we need to check. We need to check this requirement that phi of z, 0, is not equal to 0. It means that we need to take this expression, which is phi of z plus 2i squared, and we need to substitute our point 2i here. Let's do it. So it will be 2i plus 2i will be 4i squared. So it will be minus 1 over 16. Definitely it's not equal to 0. So it means that our suspicion was right. So this singularity point is indeed a pole of order m, 2. But what about residue? Let's recall the formula for residue. Residue in pole. So residue of f of z at pole z0 is given by this formula: 1 divided by, do you remember m? We used letter m. Limit when z tends to z0. Z0 is our pole of order m. Then we need to calculate the derivative of order m, or order m minus 1, m, of the m, z to the power of m minus 1. And here we have this weird expression: f of z should be multiplied by z minus z0 to the power of m first. But for this, this was a general formula, which looks a little bit daunting because it's so long. But when you're using this beautiful method 2, it turns out that the whole expression turns into phi of z, actually, phi of z. So, and I didn't write this formula in this way deliberately, because I explained to you, I had to explain you method 3 as well, which is not using this beautiful function phi of z. So it's just a general function. So in our case, our order m, not n, but m, is equal to 2. It means that 1 divided by 1 factorial is just 1. I'm sort of lazy to write it. Let's not write it. So z tends to 2i. our smaller point. And what is the order of derivative? As the order of pole m is equal to 2, so it will be derivative of the first order, just ordinary derivative. And of the expression which is phi of z, and phi of z is already here. So let's rewrite it here. 1 divided by z plus 2a squared, I squared, sorry. So now all we need to do, we need to differentiate this function, and after that we can calculate the limit. Okay, so limit, we just have to rewrite the limit all the time, of course. So what is the derivative of this function? I need to remind you this formula. So if you take a derivative of z to the power of n, it will be n times z to the power of n minus 1. In our case, we need to differentiate z in the power of minus 2. It will be minus 2 z to the power of minus 3. So in our case, it will be minus 2 divided by z plus 2i to the power of 3 cubed. In other words, sorry for this vertical line. And now calculation the limit actually is equivalent to substitution. We need to substitute z with this expression 2i, with this number 2i. Let's do it. So 2i plus 2i will be 4i cubed. So this is our residue, and I think it's better to calculate this. So 4 cubed will be 4, it will be 64. And what about I cubed? I cubed could be written as I squared times I, and I squared is minus 1, as you know. So we can do some simplification here. We can rewrite it as 1 divided by 32i. And you know what? They say that it's not good when you leave I in the denominator, but you know, I'm sort of lazy to calculate it any further. This division should be made, of course, because I'm looking ahead of one step, and I know that I'm going to multiply this residue by 2 pi I, according to my theorem. And it will be convenient to keep I here in the denominator because it will get cancelled out. That is why I'm showing this laziness. Okay, so finally, our integral, let's recall our initial integral from the expression which was dx divided by x squared plus 4 squared is equal to 2 pi and times residue of our function in this singularity point which is above the x-axis. And as you can see, this imaginary unit gets cancelled out, and we have 2 pi divided by 32, which is actually pi divided by 16. So this is our answer. And you know what? As our initial function had nothing to do with complex number theory, you should never get the complex answer here. No way, because this integral can be calculated using just conventional methods without plunging, without launching into this complex variable space, and you will never get imaginary unit using conventional methods. That is why it could be used like a good, checking technique. If you do get some I here, complex unit, it means definitely that 100% mistake. So let's check your calculations in this case. Okay, so for example 2, I'm only going to show you the beginning of example 2 because I don't think it makes sense to go over every single detail. Let's start doing example 2, which is actually question 6 from question 6a from your tutorial sheet. Let's only start with this example, and I'm not going to finish it because maybe it's too time consuming, a little bit more boring, and you should be able to do it by yourself. So in this assignment, you are given pretty similar integral from minus to plus infinity again, dx divided by x squared plus 6x plus 10. And so quite pretty similar situation. And let's start applying our algorithm then. First of all, we need to change letter x for letter z, which means that we are launching ourselves to the complex variable space. So z squared plus 6z plus 10. Then, after that, we need to check the behavior of our function at the infinity. So let's rewrite our function here. It means that we need to imagine that our z, or rather absolute value of z, tends to infinity, and then we need to realize that at infinity, when z's are really big, hugely, terribly big, the whole behavior of the whole denominator is determined only by this biggest term. So at the infinity, our conclusion, in infinity, our function behaves like this function, which corresponds to n is equal to 2 and which satisfies our theorem. So it means that it's possible to calculate this integral using this technique. Okay, next step will be to calculate singularity points of this function. Let me rewrite it again because I ran out of page again. So how can you calculate the singularity point? Very easily. You need to set your denominator equal to 0 and solve this quadratic equation. So let's calculate denominator. Oh, not discriminant. So it will be 36 minus 40. Our discriminant is minus 4. How can you take a square root from minus 4? By the way, we never discussed it. Let's discuss it now. So what you can do, you can factorize minus 4 as 4 times minus 1. This is pretty easy. Then you can write the square root above each term. And then you know the square root of 4 is obviously 2. And this is our I. This is our I. So that's how you take square roots from negative numbers. So we can pursue with our formula for square roots. So it will be minus 6 plus minus 2i divided by 2, and it could be divided by 2, minus 3 plus minus I. So we have two singularity points. Let's write them down somewhere. So Z1 is minus 3 minus I, and the other point is minus 3 plus I. Let's plot them on the complex plane. I don't think it's quite difficult for you. So the first point is minus 3 somewhere here, plus minus I. So the first point, Z1 is here, and Z2 is minus 3 again, but plus I. So it's here, Z2. And we are interested only in the point which is above x-axis, which is Z2 only. So we are throwing away our first point, and that's it. So it means that your integral, let's rewrite our integral again, x squared plus 6x plus 10 minus infinity to plus infinity will be 2 pi, according to the theorem, residue theorem, by times residue of our function f of z at the point z2. And I'm leaving it to you to finish this problem. You will have the answers in the tutorial sheet, so you won't have any problem. Okay, so we are finished with the first type of the integrals, which are integrals from minus infinity to plus infinity, and which corresponds to question 6 in our tutorial sheet. And now we are moving to our last topic. So integrals of the form integral from 0 to 2 pi, some function j which has two inputs, sinus theta or cosinus theta. They can be both here, they can be only one, it doesn't matter. So this function we denoted by j could be a function of sinus or cosinus theta, or maybe both. So again, as you can see, no hint at the complex variable theory here. But it turns out, again, it's very convenient to launch ourselves into complex space, and amazingly things become very, very easy, and you can use this result. Of course, all this reasoning is based on the theorem which has been proved in your lecture, in your study guide. We are just using this fact and we are just applying it to solve our problem. First of all, I need to remind you some very useful expressions. They are actually definitions. Do you remember such guy as sinus hyperbolic sinus of some theta? What is the definition? Definition was that this is e to the power of theta plus minus e to the power of theta divided by 2. This is actually the definition of hyperbolic sinus of theta. It's amazing that it behaves in many respects, its behavior in many respects is similar to the behavior of ordinary trigonometric sinus. Okay, what about hyperbolic cosinus of theta? It has a pretty similar definition. So it's only plus between these two terms. Okay. And also, what about trigonometrical sinus and cosinus? So sinus theta, trigonometrical ordinary sinus. You know what? Even definition looks pretty similar. Look at this. There is only a slight difference. E to the power of I times theta minus e to the power of minus I theta, and divided by 2I. As you can see, formula is pretty similar. It's not 100% the same, but pretty similar. And as for cosine of theta, it has the similar pattern which is similar to this pattern. So e to the power of I theta plus e to the power of minus I theta and divided by just 2. I haven't made any careless mistakes. There should be 2I here in the denominator for sinus and just 2 here. So there are some slight differences, but in general, the behavior is strikingly similar. So what next? As you can see, we are discussing integrals which contain this expression, either cosine of theta or sine of theta, or maybe both. And the idea is that you can substitute them with these expressions, actually, with their definitions. But what about this e to the power of I theta? Maybe you still remember this expression. We used it before when we were parameterizing the circle. So the general idea. So let's write down the idea of how to calculate this integral. Let me write this integral here again, because it's better to have it on the screen all the time. So now we are dealing with the integrals of this form. And so what is the general idea? The general idea is to substitute, make this substitution. So we are going to introduce new variable z, which is actually the complex number given in exponential form. But you can maybe you already notice that there should be a term here in front. In our case, it's 1. It means that we are going to use the contour, which is modulo z is equal to 1. This contour depicts the circle of radius 1 and with the origin as a center. If you look at these limits of integration, you realize that this is theta, which is changes from 0 to pure pi. And that is why if you decide to use this circle as a contour of the integral, you realize that theta is exactly changes from 0 to 2 pi. That is why this idea of using the contour seems to be justified. So what next? Next move, you need to know how to change your sinus theta or cosine of theta if you have them. According to the definition, so where's our cosine of theta? Let's have a look at it. Our cosine of theta is equal to this expression. Let's rewrite it here. It will be more convenient for us. Minus ei theta divided by 2. As you can see, we decided to denote this expression as z. So it could be written as z plus, what is z to the power of minus 1? It could be written as 1 divided by z. So that's what we are going to substitute instead of cosine of theta. As for sine of theta, let's rewrite this definition here. It was e to the power of e theta minus e to the power of I theta and divided by 2I. Again, let's rewrite this formula in terms of z. So it will be z minus 1 divided by z divided by 2I. And you know what? I'm going to put a frame around it, around this expression, around this expression, and around this expression. This is actually an information which you will need in your cheat sheet probably. Oh, maybe don't write this intermediate expression. Write immediately that cosine of theta is equal to this guy, sine of theta is equal to this guy, and don't waste your paper actually in your cheat sheet, because that's all you need. And so as you can see, instead of calculating this integral, which might be really difficult, we are going to make the transition into complex variable space, and we are going to use the contour integral along this contour, along this beautiful circle. But you know what? If we are going to make the substitution, we need to know what to substitute instead of the differential. So let's finish our, our preparations for the cheat sheet. Let's try and calculate this z. So we know that we are going to substitute e to the power of I theta instead of dz. And how can it be calculated? You probably remember this rule. You need to calculate the derivative of this expression times d theta. And the derivative of the exponent is the exponent itself times the derivative of this expression. So I will be in the front. E to the power of I theta d theta. And so this was the left-hand side of our expression. This is the right-hand side of our expression. So this is like an equation. And we can express d theta from here. It will be dz divided by this expression, I times I to the power of e theta. And moreover, we can realize that, we know this guy. This guy was denoted as z. So we can rewrite this dz divided by iz. And I think that we can leave this expression as it is. I think it's better to rewrite it here. So dz divided by I times z and put a frame around it. So all this information in frames is what is recommended for you to use in your cheat sheet, because I don't think it's very easy to memorize all these things. Or maybe if you have a good memory, it's no problem. So I would recommend you to put all this information in the cheat sheet, because these integrals are super actually simple, provided you know all these templates for cosine of theta, sine of theta, and so on and so on. Okay, now it's time to apply all our things which are mentioned here. So let's do one task. So I took the example from your study guide, example, which is example 4.23. I don't remember the page from study guide at least. Okay, so what is this example? So here you are given integral of from 0 to 2 pi d theta divided by 2 plus sine of theta. As you can see, you have only sinus theta. In most of the cases, you have only sinus theta or cosinus, not both of them, because if you have both of them, it would be quite a long story. So what do we need to do? We need to use all these patterns given in the previous page. So what can you do? We need to prepare the expression for sine of theta, which is z minus 1 divided by z divided by 2i. We also need expression for our differential, which was calculated before dz divided by I times z. And that's it. That's it. We don't have anything else here. And we already know that we are going to make a transition to the contour integral along this contour. So let's do it. So I'm putting it here. So instead of integral from 0 to 2 pi, I'm going to write integral, contour integral along closed contour z modulo z is equal to 1. Instead of the differential of theta, I'm going to substitute this guy, dz divided by iz. And now 2 plus, and instead of sine of theta, I'm going to substitute this guy, z minus 1 divided by z by 2i. And that's it. Now, all which is left for us to do is just to simplify this expression. And finally, we end up having just quite a standard task, calculation of the closed contour integral, and our beautiful residue theorem. So let's start doing this. I think that it's better to simplify this expression first, and after that we could move to the whole denominator. So let's start. So now comes the boring part. We already know what to do. There's just no need to do all these technicalities. So this expression could be written as z squared minus 1 divided by 2iz. 2iz. Again, this was the first movement. Then we need to simplify the whole denominator. I think it can be rewritten as, okay, I'm rewriting denominator first. And now this should be multiplied by this, 2iz. So z squared plus 4iz minus 1 divided by this denominator, 2iz. Now we have like 4 levels in our fraction, and that is why we need to simplify it further. So what else can we do? We can realize that we can cancel out these two expressions. Iz and z gets cancelled out, and this divided by 2 gets moved to the numerator. I can actually put maybe 2 in front of the integral. Maybe it will be more convenient. So dz divided by this expression, z squared minus or plus 4iz minus 1. And now you realize that, oh, it's pretty old and familiar task. It's just an ordinary contour integral. The contour is given, and all I need to do, maybe it's better to use the residue theorem. Maybe Cauchy integral formula. It's, that's what you like more. Okay, so let's find singularity points. So our contour is here. Our contour is here. This is a circle with the radius 1 minus r. And we need to determine which of the singularity points are inside the circle, according to our famous residue theorem. Okay, let's find singularity points. Z squared plus 4iz minus 1 is equal to 0. Again, this is a typical square differential so we can find discriminant. Discriminant is 4i squared plus 4. It will give us minus 16 plus 4. It will be minus 12. And we just discussed how to take square roots of these negative numbers. We can rewrite minus 12 as 12 times minus 1. And so it will be square root of 12 times imaginary unit y. But I think that square root of 12 could be simplified even further. If you imagine then 12 is 4 times 3, so it will be 2 square root of 3 times I. So, and now we need to calculate our roots of this equation. So it will be minus 4i plus minus this discriminant, 2 square root of 3 times I, divided by 2. We can simplify it a little by dividing by 2, minus 2i plus minus square root of 3 times I. And we can even pull out I from this expression. So we'll have minus 2 plus minus square root of 3 times I. Actually, we got purely imaginary numbers. Let's write down our singularity points separately. So the first one will be minus 2 minus square root of 3 times I. And the second one will be, maybe it's more convenient to write it in this way, square root of 3 minus 2. Looks a little bit more beautiful. Okay, so we do have our singularity points. And now we need to determine which of them lies inside the circle. So what is this number? Minus 2 minus square root of 3. Square root of 3 is approximately 1.5. So it will be minus 3.5. It's definitely somewhere here. So Z1 is outside the circle. That is why we are not interested in this point. What about this one? This will be 1.5 approximately. Minus 2, it will be minus 0.5. So it's definitely inside the circle. So now we know how to finish our task. Our integral will be equal to 2 pi I times residue of our function. In which point? In the point Z1, which is inside the circle. So that's how our residue theorem looks like applied to our particular task. Okay, so we need to calculate the residue of our function in this point, which is z2. Let's copy it to the new page. So our function, I think it's better to take the integral again, because otherwise I will forget about it. So our function is 2 divided by z squared plus 4iz minus 1. It's better to rewrite it in a factorized form, of course. Let's do it. So the first root was minus. So let's write it. Z minus the first root. The first root was minus 2 minus square root of 3 times I. And the second term will be z minus the second root. Minus square root of 3 minus 2 times I. So this factorized form is much more convenient for determining the type of singularity. Again, we know that we are dealing with the point which is z is equal to square root of 3 minus 2 times I. We are interested in residue in this point. And we already have the suspicion that this might be a pole. Maybe this is a simple pole, the pole of order 1. But we need to make sure that this is true. So we need to look at this function from the point of view of this structure, phi of z divided by z minus z0 to some power n. We need to compare our function with this template. And so what can we see? Of course, this term corresponds to this term in the denominator. So our suspicion, therefore, is that our pole should be of power of order 1, because this brackets, this expression in the brackets is in the power of 1. But before making this conclusion, we need to make sure that our expression, which corresponds to phi of z, and this is this part, so this yellow part corresponds to phi of z. So phi in this point is not equal to 0. Let's check it. So checking is very important. Let's check. So phi of z0, in our case phi looks like 2 divided by this expression. You know what, it's better to rewrite this expression with pluses, because there are too many minuses there. That plus 2 plus square root of 3 times I looks much nicer. And we need to substitute our singularity point, square root of 3 minus 2 times I. As you can see, too many roots here. Okay, so let's substitute it here. Square root of 3 minus 2 times I, and I'm rewriting this term, plus 2 plus square root of 3 times I. So what can we have here? What do we have here? So we have this, if you do all the multiplication, you will realize that minus 2i and plus 2i here get cancelled out. And these guys, which has square root, they get added together. So 2 square root of 3 times I. It will be 1 divided by I square root of 3, which is actually not 0. Of course, I haven't done the division of two complex numbers, but it's not necessary to realize that it's not 0. Okay, so we are very lucky. So our conclusion, that is this point, this singular point, is simple pole. Simple pole, that means that pole of order 1. Pole of order 1. And now all is left for us to do. We need to calculate the residue in this point. But this is going to be super easy, because this is a simple pole. So what about residue? Residue of f of z at this point, let me write it down, this point, square root of 3 minus 2i is equal to what? 1 divided by m minus 1 factorial. I'm going to write this formula again. Limit when z tends to this z0, this is z0. And what is the order of our derivative? Usually it's a derivative of order m minus 1. But m minus 1 in our case will be 1 minus 1, which is 0. And derivative of order 0 means no derivative at all. So we need to write just phi of z here. You remember we discussed it before in this tutorial, that this is actually phi of z. So this is 1, of course, because 1 minus 1 will be 0. 0 factorial is 1. So all we need to do, we need to substitute our current singularity point into our phi of z. And phi of z was this yellow expression in the previous page. But you know what? We already done it before. Of course, I'm rewriting this expression once again. But actually, we did it before. When we were checking this equation that phi of z is not equal to 0, we actually calculated the residue. So we can just copy it from there. So residue in this point is given by this number. And again, I'm showing a little bit of laziness, because of course I haven't completed this, this number. You should have done the division, but it's not necessarily necessary, because in this particular setting you are going to multiply this expression by 2 pi I, and it's more convenient to have I here. So now it's time to finish our task at last. So let me write it at the beginning of our task. Where was it? Almost this page, I'm afraid, already. So it was, that's one example. So our example was integral from 0 to 2 pi d theta divided by 2 plus sinus theta. And it turns out that it is equal to 2 pi I times this residue at this point, which is equal to this expression. And it, as I discussed before, it's very convenient that we have I both in denominator and numerator. We can easily cancel it out. And of course, we can simplify this expression, but maybe it's not absolutely necessary. I just do it out of habit. So we don't have any I here at all, which is the indication that we haven't done any terrible mistakes, because our initial integral didn't contain any complexity and didn't contain any imaginary unit. It means the answer shouldn't contain any imaginary unit as well. We just use the complex variable theory as a very convenient tool for calculating this very difficult integral. By the way, it's not very easy integral, simple integral. But then we sort of got back to our real space. So that's it. This was the last part of the last tutorial 12.